A magnetic field that's strong, it could wipe every credit card on the planet, even from as far away as the moon. That's the power of a magnetar. It's a dead star. It bends the rules of reality. So, how do these cosmic monsters create the strongest magnetic forces we know? We have to look at how they're born. It's violent chaos. And inside them, there's a strange quantum soup at the heart. That's what creates a magnet so powerful it can twist space itself. That final collapse is where the change really starts. A giant star runs out of fuel, and its own gravity, the force it's been fighting for millions of years, finally takes over. The core gives way. It just implodes. All that mass from a star much bigger than our sun, suddenly rushing inward, crushing down into a space no bigger than a city. It happens in less than a heartbeat. The energy released is almost impossible to grasp. It powers a shockwave that tears the star apart from the inside. We see that as a supernova, a flash of light that can outshine a whole galaxy. It's a stellar forge of unbelievable power, and what it makes in that instant is something new. The collapsing core gets so dense that protons and electrons are forced together. They merge into neutrons. The result is a neutron star. You take the entire mass of our sun and squeeze it into a ball just 12 miles across. The matter inside is packed so tight that a single teaspoon of it would weigh as much as a mountain. That's the raw material, the incredibly dense, rapidly spinning remnant left behind after the fire fades. That violent birth is the essential first step. You can't have a magnetar without first creating that neutron star seed, born from one of the most energetic events there is. But not every neutron star becomes a magnetic monster. Something extra has to happen in that chaos. That neutron star we just talked about, a city-sized ball of nuclear matter, is already a cosmic powerhouse. Its magnetic field is staggering. A typical pulsar, a spinning neutron star that beams radiation, has a field 1 trillion times stronger than Earth's. It's a force so immense it shapes the space around it. But that's just the ordinary, that's just the baseline. For a magnetar, that incredible strength is just the starting point. A magnetar's magnetic field is another 1,000 times more powerful. To grasp that scale, think of the difference between a tiny refrigerator magnet and the magnetic containment field inside an experimental fusion reactor. A field so strong it can hold a star's worth of plasma. That's the leap from a pulsar to a magnetar. We're talking about magnetic fields so intense they don't just influence matter. They warp the very structure of reality, bending the fabric of space and time around the star. This isn't a difference of degree, it's a difference of kind. So what happened? In that same supernova forge, under that same blanket of chaos, what special recipe creates a magnetic monster instead of a merely powerful pulsar? The secret isn't in the ingredients, but in the mixing. It's all about the spin. That spin is everything. A figure skater pulls their arms in and they spin faster. Their mass compresses and the rotation speeds up. Now take that idea, but replace the skater with a collapsing stellar core. Replace the ice with a fluid. A fluid of unbelievably hot conductive neutrons. That's the key. It's a principle. It powers magnetism across the cosmos, from our own planet to the hearts of stars. It's called the Dynamo Effect. Our Earth isn't a permanent magnet. Its magnetic field is alive. It's generated by an engine deep within. Molten iron, heated by the planet's inner heart, swirls in the outer core. That motion of a conductive fluid, that kinetic energy, gets transformed. It self-organizes into vast rolling currents, currents that generate our planet's magnetic shield. It's a process that turns motion into magnetism. Stars do this too with churning plasma. But for a magnetar, the dynamo has to be something else. The material inside that newborn neutron star isn't just hot plasma. It's a neutron superfluid, a quantum material with zero friction, and it's swirling at speeds that approach a significant fraction of light itself. The kinetic energy here is beyond planetary. Beyond stellar, it is the raw, concentrated spin of a stellar corpse, trapped and churning in a city-sized crucible. This is the hyper-powered dynamo. The first crucial piece, it suggests that in its first few seconds, the magnetar's interior is a maelstrom, a turbulent motion on a scale we can barely model. That chaos is the engine, but an engine needs fuel, and for this cosmic dynamo, the fuel is a spin so rapid it defies belief. That furious spin is the second thing you need. A neutron star, when it's born, can be spinning at an impossible speed, a full rotation in just a few thousandths of a second. If the Earth spun that fast, a day would be shorter than a blink. It's not just fast, it's a blur right at the edge of physics, and that speed comes straight from its birth. The core collapses, pulls everything in. Like a skater pulling in their arms, that compression forces the spin to accelerate into a frenzy. All that rotational energy, that kinetic fury, goes right into the quantum fluid inside the star. It becomes the fuel, the dynamo fuel. Basically, the faster this conductive material swirls, the more it can stretch and twist the magnetic field lines that are already there. It's like taking a loose rubber band and winding it tight around your fingers. Rapidly, the energy from the motion gets stored in the magnetic field, amplifying it to staggering levels. This spin hypothesis is compelling. It gives a clear mechanism for how a field goes from immense to universe-leading. But there's a catch. Spin alone doesn't make a magnetar. We see plenty of fast pulsars. They're powerful, but they're not magnetars. Their fields are strong, but not that strong. So something's missing. The spin provides the energy, but the star's interior has to act as a perfect conductor, a flawless transformer, to take that chaotic motion and channel it into a coherent, organized magnetic monster. The spin sets the stage, but the real drama is in the star's strange heart. The inside of a star at that moment is just a storm, unimaginable, and in those first few seconds, the new neutron star isn't quiet. It's not a solid ball, it's a seething cauldron. You have to remember the heat from the supernova. The energy that just tore the star apart, that heat doesn't vanish. It floods the interior. It's trapped there inside that dense shell, the star's crust. And that creates a temperature difference so extreme it sets the whole quantum fluid into motion. Violent, rolling motion. It's convection, but on a nuclear scale. Think of a pot of water boiling. Heat at the bottom makes the water less dense, so it rises. Cooler water from the top sinks, creates a circular churn. Now replace the water, make it a super hot, electrically conductive soup, neutrons, protons, electrons, and crank the heat to billions of degrees. This isn't a gentle simmer. It's a chaotic, turbulent overturning of the star's very heart, and that convective chaos, it's the perfect engine for a magnetic dynamo. As those immense bubbles of hot fluid rise and the cooler ones sink, they don't move in straight lines. The star's rotation, that furious spin, it twists these motions, it shears them, stretches them, and tangled in this fluid are the faint, primordial magnetic field lines. Leftover threads from the star that died. The convective motion grabs these threads, it pulls them, it winds them up like twisting strands of spaghetti around a fork. With every turn, every shear, the motion transfers energy, the thermal energy from the heat, the kinetic energy from the spin. It all gets pumped directly into the magnetic field. It amplifies it exponentially. Some of the most advanced models suggest this phase, this hypercharged convective phase, is incredibly brief. It might only last 10 or 20 seconds. After the core collapses, in cosmic terms, that's less than a blink, but for a magnetar, that blink is everything. It's the defining moment. In that short, violent window, the dynamo does its work. It takes the raw, chaotic energies of birth and forges them into an organized, coherent magnetic field of legendary strength. This process sets the magnetic blueprint for the entire life of the star, a blueprint written in a fury of heat and motion, and then frozen in place for the next 10,000 years. The storm ends. The interior begins to cool, to settle, but the magnetic monster it created that remains. That convective storm can only get you so far. To reach magnetar levels, you need a second kind of chaos. A more precise one. It needs a tug of war inside itself. That's differential rotation, different parts of the star spinning at different speeds. You see it on the sun. The equator spins faster than the poles, a fluid sphere that hasn't settled into one motion. Now take that idea and inject it with a supernova's energy. Apply it to the newborn neutron star. In those first moments, the star isn't uniform. It has layers, a thin, solid crust starting to form, an outer core of neutrons and protons, a quantum soup, and a deeper inner core of matter so dense we can only guess. These layers can spin at wildly different rates. The crust might try to slow down while the fluid interior keeps whirling. Or one fluid layer drags against another, creating a shear, a zone of extreme velocity difference. That shear is where the monstrous magnetism happens. Picture a magnetic field line like a strand of elastic, frozen into that hyperconductive fluid. Grab one end and pull it. The other end is anchored. As the fluid shears, the field line stretches, drawn out, like pulling a rubber band until it's thin and taut. This stretching does something. It doesn't just make the line longer. It concentrates the magnetic energy along its length. The energy density skyrockets, and in that hyper-dense, superconducting environment, there's almost no resistance. No friction to slow it down, so the shearing can continue, winding the magnetic field tighter. It's a feedback loop. Motion creates a stronger field. A stronger field influences the motion, which amplifies the field further. Differential rotation acts like a cosmic amplifier. It takes the strong field from the convective dynamo and cranks the dial past a normal pulsar into magnetar territory. It's the difference between a powerful river current and that same current forced through a narrow, twisting canyon. The energy becomes focused, violent, unimaginably intense. This process, in that brief window after birth, could be the final step, the push from merely powerful into a true magnetic monster. But even this has a limit. A star can't spin infinitely fast. It can't shear forever. Something has to stop it, and what stops it might be the strangest part. The star's own matter, forced into a state that defies everything. The storm inside starts to settle, but what it leaves behind isn't like anything on Earth. To lock a magnetic field that strong in place, you have to look at the star's deepest heart, a place where the rules aren't chemistry anymore, they're quantum physics. It's not just a ball of neutrons, it's a landscape of exotic matter. When you crush atomic nuclei past a certain point, the particles themselves change. Protons and neutrons under that pressure can dissolve. Their walls break down. You get a sea of free quarks and gluons, the fundamental building blocks. In that environment, even stranger particles can form, like hyperions. They contain strange quarks. Some theories say the whole core could become one continuous blob of this strange quark matter. It sounds like science fiction, but the mathematics says it's possible. Inside these extremes, this exotic quantum soup has two properties that are critical for a magnetar. First, it becomes a superfluid. It flows with zero friction, no viscosity. Think of it as the ultimate slick surface. A vortex in that fluid would spin forever, never slowing. Second, and more important for magnetism, this soup is a superconductor. In an ordinary wire, electric currents face resistance. They lose energy as heat. But in a superconductor, once a current starts, it just keeps going, indefinitely, no loss, no energy drain. Now combine these two ideas. You have a frictionless, superconducting fluid, churning after that immense convective storm. The magnetic field lines from the star's birth aren't just floating in this medium. They're frozen into it, trapped, because the superconductor expels magnetic fields from most of its bulk, but it can also trap them. In microscopic whirlpools of magnetic flux, these whirlpools, these tiny tornadoes of magnetism, get pinned in place by the star's dense matter. They can't move. They can't dissipate. The superconductor won't let the energy escape as heat. The superfluid won't let it be slowed by friction. That creates the perfect environment for preserving magnetic energy. All that monstrous strength forged in the first seconds, from spin and shear and chaos, doesn't slowly leak away. It gets bottled, concentrated and preserved inside this quantum landscape for eons. The exotic core acts less like a storage battery and more like a flywheel of pure magnetism, spinning in a vacuum, losing energy at an almost imperceptibly slow rate. That's why magnetars can still unleash catastrophic starquakes and brilliant flares tens of thousands of years after their violent birth. The engine has quieted. But the fuel it produced, that coiled magnetic spring, is still there, trapped in a state of matter so strange it lets the impossible endure. The quantum bottle seals the energy away. But before that happens, there's one last step. It's almost mechanical. It happens in the blink of an eye during the collapse itself. It's a law of physics. Magnetic flux has to be conserved. You can think of flux as the number of magnetic field lines passing through an area. You can move them, you can bend them. But you can't destroy them. If you take a region with a magnetic field and you squeeze it, compress it down, those field lines have to go somewhere. They get crowded together. Their density goes up, and the strength of the magnetic field is just a measure of that density. More lines in a tighter space means a much more powerful field. Now the dying star, its core before the collapse, is already magnetized. Every star has a magnetic field. This core is enormous, larger than our planet. And then gravity wins, it implodes, that planet-sized core gets crushed, down into a sphere only about 12 miles across, 20 kilometers. The volume shrinks by a factor of billions. And the magnetic field trapped inside gets squeezed with it. Those field lines are frozen into the plasma of the collapsing core. They have to follow the matter. They get dragged inward, packed into a space a billion times smaller, so their density skyrockets and the field strength skyrockets by that same staggering factor. In an instant, a stellar magnetic field gets amplified into something monstrous. This isn't the dynamo yet. This isn't spin adding new energy. This is pure geometry. Physics taking the field that was already there and concentrating it, like focusing sunlight through a magnifying glass into a searing point. This compressed, billion-fold stronger field becomes the essential seed. The initial spark, without this amplification from flux conservation, the newborn neutron star would start with a much weaker baseline. The convective dynamo that comes next, the differential rotation, would have far less to work with. They'd be trying to amplify a whisper into a scream, but because of this brutal compression, they start with a roar, a magnetic field already pushed to extremes. Then, in those next few chaotic seconds, the hypercharged dynamo takes over. It grabs this intensely concentrated seed field, and it uses the star's furious spin, the internal shearing, like a cosmic crank, to wind it tighter, to pump it full of even more energy, transforming that powerful roar into the deafening scream of a true magnetar. The collapse provides the spark. The dynamo builds the fire, and the star's exotic heart makes sure the blaze burns for millennia. We call it the Proto-Magnetar Model. It's a single story, a unified one. It doesn't choose just one cause. It says all of them are necessary, all at the same time, in this perfect, fleeting alignment. It starts with the right kind of parent star. One that was already spinning fast with its own strong magnetic field. When that star reaches its end, the collapse happens. It does its brutal work. And it compresses that inherited magnetic field by a factor of billions in an instant. That's the powerful seed. Then, in the first minute of this new object's life, the trapped heat from the supernova takes over. It turns the interior into a churning convective maelstrom, a quantum fluid in violent, rolling motion. At the same time, the different layers of this newborn star are spinning at wildly different speeds. That differential rotation shears everything, it stretches everything. Now you place that intensely concentrated seed field directly into this environment. A hyperconductive, superfluid core caught between turbulent convection and extreme shearing. This combination acts as a dynamo of almost perfect efficiency. It takes the raw, chaotic energies of spin and heat and channels them directly. It pumps that energy relentlessly into the magnetic field, winding it tighter and tighter, amplifying it from an already immense level into the legendary strength of a magnetar. The model is beautiful in its completeness. It ties the star's initial conditions, the violent physics of collapse, and the strange quantum rules of matter into one coherent narrative. It explains why magnetars are so rare. You don't just need a star to die. You need a star with the right spin, the right magnetic heritage to die in just the right way. To create that perfect temporary storm inside, a storm that forges a magnetic monster in less than a minute. This is our most complete theoretical picture. A blueprint for how the universe builds its ultimate magnets, but a theory, no matter how elegant, needs proof. It needs to make predictions we can see from across the galaxy. We used to think magnetars only came from supernova. That was the story. One star explodes, and in the aftermath, this incredibly magnetic object is left behind. But now there's another possibility, a more violent one, the collision of two neutron stars. Picture two of them, each the size of a city but heavier than our sun, in a decaying orbit. They spiral for millions of years and then they finally touch. It's not a gentle bump. They tear each other apart in an event called a kilonova. That explosion is powerful enough to create heavy elements like gold. But in the middle of that chaos, something else might form, a hypermassive neutron star. It's a temporary thing. The combined mass is too great, so it can't support itself for long. It might last only a few hundred milliseconds, just a cosmic heartbeat, but in that instant, the physics is extreme. You have these two objects, each with a magnetic field 1 trillion times stronger than Earth's, crashing together. Their fields get tangled and stretched in the turbulent debris. The rotation is wild as the two cores merge into one lopsided, spinning mass. This environment, according to simulations, could act as a dynamo. An incredibly fast one. It takes the existing strong fields and amplifies them by a factor of 1,000 or more. So for that brief moment before it collapses into a black hole, this remnant could shine with a magnetic field rivaling a classic magnetar's. A magnetar born not from a death but from a violent merger. A flash of magnetic brilliance that vanishes almost immediately. This idea is a compelling alternative, especially for magnetars found in dense places like globular clusters, where stars are packed close and collisions are more likely. It shows the universe has more than one workshop, more than one way to build these extreme objects. The supernova path might be the primary one, creating magnetars that last for millennia. But the merger path could be a secondary channel, a way to produce something even more transient and unbelievably powerful. It means the story of their formation has more than one chapter, each written in violence and each leaving behind that signature of coiled magnetic fury. The blueprint is elegant in theory, but it's just equations and simulations. To prove it, you have to reach across the galaxy and take a measurement. You have to observe the force itself. We can't go to a magnetar. we can't put a probe on it. That probe would be torn apart long before it got close. So the question is how to measure a magnetic field from 10,000 light-years away. Astronomers use an indirect method. They read the story in the magnetar's light. These objects aren't dark. They glow fiercely, but not in light we can see. Their radiation is in the high-energy part of the spectrum, in X-rays and gamma rays, and this emission isn't a steady beacon. It carries a fingerprint, a hidden code that reveals the magnetic environment it came from. The key to breaking that code is how charged particles behave in a magnetic field. Think of an electron caught in a magnetar's field. It doesn't travel in a straight line. It spirals, it gyrates, corkscrewing along the magnetic field lines, and as it does this, it can emit or absorb radiation. But here's the crucial part. It doesn't do this at just any energy. The spiraling motion forces it to interact with light at one specific frequency, directly tied to the strength of the magnetic field. It's like a tuning fork for magnetism, a fork that only vibrates at one precise pitch. When astronomers point telescopes like XMM Newton or New Star at a magnetar, they don't just see a blur of X-rays. They spread that light out into a spectrum, breaking it down by energy like a prism makes a rainbow. In that high-energy rainbow, they look for dark lines or bright lines at specific energies. These are the signatures of that spiraling electron interaction. Scientists call them cyclotron resonance scattering features. It's a complex name for a simple concept. It's the direct imprint of the magnetic field on the light. By measuring the precise energy of these spectral lines, astronomers can do a direct calculation. They plug that number into a physics equation, and out comes another number, the strength of the magnetic field at the magnetar's surface. It turns a telescope from a camera into a cosmic magnetometer, a device that can measure a magnetic force from halfway across the galaxy. This isn't inference, it's empirical proof. When those calculations return a number with 28 zeros, confirming a field 1,000 trillion times stronger than Earth's, the theoretical monster becomes a measured reality. We aren't just imagining these magnetic titans, we are reading their strength in the very light they cast into the void. The measured reality is a monster under constant strain. A magnetar's magnetic field isn't a static cage. It's a living, writhing force, and it's trying to tear its own home apart. The star's crust is this bizarre material, a crystalline lattice of atomic nuclei squeezed into a solid shell maybe a kilometer thick, but it's unbelievably strong, 100 billion times stronger than steel. And even that supermaterial has its limits. The magnetic field running through it is under immense tension, like billions of rubber bands all stretched to the breaking point, woven through that thin crust. They pull, they twist, they store colossal energy, and like any overstressed structure, something eventually gives. The crust cracks. It's a starquake. But this isn't a planetary tremor. It's a seismic event on a nuclear scale. A shift of just a few centimeters in that ultra-dense crust releases more energy than the sun puts out in 100,000 years. All in a fraction of a second. That energy doesn't just shake the star, it violently shakes the magnetic field lines anchored to it, like plucking a cosmic guitar string made of pure force. The vibration sends a storm of charged particles racing along the twisted field lines. They collide, they're accelerated to nearly light speed, and in that chaotic frenzy, they scream. They release their energy as the highest energy radiation in the universe, a blinding flash of X-rays and gamma rays. We've seen these screams from across the galaxy. On December 27, 2004, a wave of radiation swept over our solar system. It came from a magnetar 50,000 light-years away on the far side of the Milky Way. For 0.2 of a second, this single object outshone the full moon. In gamma rays, it was brighter than anything else in the observable universe. It ionized atoms in Earth's upper atmosphere, affecting long-range radio communications. The energy was so vast that if it had happened within 10 light-years of us, it could have severely damaged our planet's ozone layer. That was a giant flare. The most violent expression of a magnetar's magnetic stress, a direct signal that the theoretical forces we calculate are very, very real, that they can reach across cosmic distances to tap us on the shoulder. But not all outbursts are that extreme. More common are the short bursts, brief, intense spikes of X-rays that last only a heartbeat. These are likely smaller crust fractures or sudden rearrangements of the magnetic field itself. Each one is a pressure valve, releasing a little of the immense stress building inside the star. Together, these starquakes and bursts form a language. They're the telltale signs we can observe, the cracking sounds and flashes of light from a celestial object wrestling with forces it can barely contain. Every time our telescopes catch one of these events, it's a confirmation. We're listening to the magnetic monster strain against its own incredible power. For years, those flashes were a complete mystery. They came from fixed points, but they weren't like anything else we knew. They gave off gamma rays, but these were softer, lower energy than the big bursts from deep space. And they repeated. An object would flare, go quiet, then flare again months or years later. Astronomers called them soft gamma repeaters, SGR, and no one knew what they were. What kind of object could do that, produce these powerful but tempered explosions over and over? The theories didn't work. They couldn't be normal pulsars. Their spin was too slow. They couldn't be black holes pulling in material. The behavior was all wrong. The answer was in the timing of the bursts and the quiet between them. When they finally found the exact locations of these SGRs, they saw something. Each one was sitting right in the middle of a supernova remnant, the leftover shell from a star's explosion. That meant the object was young, a newborn stellar corpse, and when they measured its spin, they found it was slowing down, fast. A pulsar's spin down is a clock showing energy loss. For an SGR, that clock was running down incredibly fast. That rapid spin down was the clue. The only thing powerful enough to put such a brake on a city-sized ball of nuclear matter, to slow its spin that dramatically, was an unbelievably strong magnetic field. The field acts like a brake. It saps the star's spin energy, turns it into a wind of particles and radiation. The math was clear. To explain the slow spin and the fast slowdown, the magnetic field had to be in the magnetar range, quadrillions of times stronger than Earth's. Then the bizarre behavior made sense. The soft gamma-ray bursts were starquakes, the crust cracking under magnetic stress. The repetition was just this coiled spring of magnetism, releasing pent-up energy over and over. The SGR wasn't a mystery anymore. It was proof, the Rosetta Stone. It translated theory into reality. Here were objects behaving exactly as a magnetar should. Their slow spins, their rapid spin downs, their violent, repeating outbursts. All of it pointed to one source, an ultra-strong magnetic field, alive and writhing, making itself known across the galaxy. The monster had a voice, and we had finally learned to understand it. Some magnetic monsters don't announce themselves with a violent flash. They speak in whispers. You find them in the X-ray sky. They pulse with a steady rhythm, shining brightly in that high-energy light. But they spin too slowly to be ordinary pulsars. Their rotational energy, the power source for a typical neutron star's beacon, is almost gone. It's far too weak to explain the intense X-ray glow we see. For decades, these objects were an enigma. Astronomers named them anomalous X-ray pulsars. The name itself was a confession. They were anomalous, they pulsed, but they weren't powered by spin. So what was lighting them up? The answer was hiding in their quiet, relentless glow. These AXPs are magnetars in a different mood. They are the calm, steady-state version of the magnetic monster. They've passed through their most violent youth. The giant flares and frequent starquakes have subsided. but their magnetic field, though no longer causing catastrophic ruptures, is still unimaginably strong. And it is still decaying, slowly releasing its pent-up energy over millennia. This magnetic decay is the power source. The star's own monstrous magnetism, slowly leaking away, heats the interior and the surface. That heat then radiates away as the bright, steady X-ray emission we observe. It's like a banked fire, glowing with the residual heat from a blaze that once raged. This gives us a different window into the magnetar's heart, perhaps an even clearer one. Without the drama of giant flares obscuring the view, scientists can measure the star's properties with precision. They watch its slow, steady spin down. They measure the exact energy of its X-ray glow, and from those two quiet numbers, they can perform a direct calculation. The energy being lost as X-rays must come from somewhere. Since it's not coming from rotation, it must be coming from the decay of the magnetic field itself. By measuring the output, you can infer the strength of the source. It's like seeing how brightly an ember glows and knowing exactly how hot the fire once was. In this calm state, the theoretical predictions of magnetar strength find their cleanest confirmation. The spin-down rates, the X-ray luminosities, they all point to the same staggering number. A magnetic field 1,000 trillion times stronger than Earth's. The whisper tells the same story as the scream. It just uses a different tone. By studying these quiet giants, astronomers are piecing together the later chapters of a magnetar's life. They are watching the magnetic spring, wound so tight at birth, slowly and silently unwind. Even the most powerful magnetic monster can't rage forever. That immense field, forged in a supernova and bottled in a quantum state, isn't permanent. It's a reservoir of energy, and like any reservoir, it slowly empties. This process is magnetic decay, the slow, inevitable fading of a giant. It happens over thousands of years, a leisurely pace for a star. But it's the engine behind the steady glow we see from the quiet ones, the anomalous X-ray pulsars. Their brilliant X-rays aren't a sign of violent youth, but of a long, patient release. The star is glowing with the heat of its own fading magnetism. The decay happens through a few different channels, each a leak in the perfect magnetic bottle. In the star's solid crust, the lattice of atomic nuclei, electric currents are flowing. These currents sustain the external field, but this crust, while incredibly dense, isn't a perfect conductor. It has a tiny amount of electrical resistance. Over centuries, that resistance causes the currents to lose energy, little by little, converted into heat that warms the star from within. It's a slow drain, like a battery left on a shelf. Deeper down, in the exotic superconducting core, the decay mechanism is stranger. Those microscopic whirlpools of magnetic flux, pinned in the quantum fluid, they're not completely static. They can slowly drift, they can migrate through the superfluid, and when two whirlpools with opposite magnetic polarity meet, they can annihilate each other. Cancel out. When that happens, the magnetic energy stored in them doesn't vanish. It transforms. It becomes thermal energy, adding more heat to the star's interior. This process is like the slow, quiet popping of billions of tiny magnetic bubbles, each pop releasing a whisper of warmth trapped for millennia. This relentless, slow conversion of magnetic energy into heat is what powers the persistent glow of an XP. The star is quite literally shining with the light of its own decaying power. By measuring the exact brightness and temperature of that X-ray glow, and by watching how quickly the star's spin continues to slow down, astronomers can calculate the rate of this magnetic decay. They can estimate how much magnetic energy is being lost each year, and from that they can work backwards. They can estimate the magnetar's age. A younger magnetar will have a stronger field, spin down faster, and often be more active with bursts. An older one will be calmer, its glow a bit dimmer, its spin more sedate. It's a cosmic clock ticking down with the slow unwinding of a magnetic spring. This decay has an ultimate end. After tens of thousands of years, perhaps 100,000, the magnetic field will have faded enough. It will still be staggeringly strong, 1,000,000,000,000 times Earth's field or more, putting it in the realm of a powerful, ordinary pulsar. But it will no longer be a magnetar. The star will have crossed a threshold, the internal stresses will ease, the catastrophic starquakes will cease. The monster will have settled into a quieter, though still unimaginably extreme, old age. Studying this decay isn't just about watching an object fade. It's about understanding the entire life cycle of magnetic energy in the most intense environments the universe can build. It traces the journey of a force from its violent, chaotic birth through its brilliant, dominant prime to its long, slow sigh into a more stable state. Every whisper of X-ray light tells a chapter of that story. There's a ceiling to this power, a wall built into reality itself. The magnetic fields around the most extreme magnetars, they brush up against a fundamental quantum boundary. It's called the Schwinger Limit. That's the point where a magnetic field stops being just a force. It becomes an environment, so intense it can directly manipulate the quantum vacuum. Because empty space, according to our best theories, isn't actually empty. It's a seething sea of potential, virtual particles, electrons and their antimatter twins, positrons. They flicker in and out of existence. They borrow energy from the vacuum for an immeasurably short time, then annihilate and give it back. It's a quantum loan. Always repaid instantly, but near a magnetar, the rules of that loan change. The magnetic field is so powerful it can provide the energy. It can reach into that quantum sea and pull those virtual particles into reality. Permanently, an electron and a positron created from nothing but pure magnetic force. This isn't science fiction. It's a direct prediction of quantum electrodynamics. Our theory of how light and matter interact. At the Schwinger limit, the magnetic field is strong enough to spontaneously generate matter from the void. And that has profound consequences for how radiation behaves around the star. Light itself, traveling through this magnetized vacuum, doesn't move the same way. Its properties can be altered. Some theories even suggest that at these extremes, the vacuum of space itself could undergo a phase change. It could become a magnetic superconductor, a perfect conduit for magnetic fields, changing how they're structured and how they decay. Magnetars are the only places in the universe, as far as we know, where conditions naturally approach this quantum cliff edge. They're cosmic laboratories, testing the laws of physics under stresses we could never hope to create on Earth. Every calculation, every model of their interiors and their magnetospheres pushes our most fundamental theories to their absolute breaking point. We're watching to see if the equations hold, or if, in the presence of such concentrated power, nature reveals a new set of rules we have yet to imagine. The space around a magnetar isn't empty, it's a cage made of pure force, an atmosphere woven from magnetic field lines so strong they dictate reality. That's the magnetosphere, and in there physics becomes extreme. The magnetic field is the ruler. Gravity, the force that holds stars together, is minor here. The magnetic pressure dominates everything. It creates a tortured architecture. The field lines aren't simple loops from pole to pole. They're twisted, braided, knotted by the star's rotation and the shifting of its crust. Picture a ball of yarn after a cat's gotten to it, but each thread is a conduit of unimaginable power. This tangled web is the stage. Into this twisted cage, charged particles are born, electrons and positrons, ripped from the star's surface or spawned from the energy of the field itself. They don't drift, they're catapulted, accelerated along those contorted magnetic highways to velocities near the speed of light. As they spiral and slam along these paths, they release their energy. They release it in a scream of radiation, primarily in X-rays. That's why magnetars glow so fiercely in the X-ray sky. even when they're quiet. Their entire magnetosphere is a continuous particle accelerator, shining with the light of matter pushed to its limits. But this twisted architecture is unstable. The field lines are wound like over-tightened springs. They store colossal energy. They want to snap back into a simpler, lower energy state. In some models, the twisting reaches a breaking point. The field lines can suddenly reconfigure. They break and reconnect. It's a process we see on our own sun during solar flares. Magnetic energy converted into heat, light, and particle acceleration. On a magnetar, this same process is scaled up by billions. A single reconnection event in that tortured magnetosphere can release more energy than our sun will emit in its entire 10 billion-year lifetime. All in a fraction of a second. That's the leading explanation for the giant flares, that catastrophic snap of magnetic field lines deep within the star's atmosphere. It unleashes a firestorm, a blast of radiation and a cloud of relativistic particles expanding outward at nearly light speed. The magnetosphere itself is the trigger and the amplifier. It takes the stress building within the star and focuses it into a single, universe-brightening flash. This dynamic atmosphere is the direct interface. It's where the internal turmoil of the magnetic monster meets the cold vacuum of space, and it transforms that hidden struggle, transforms it into the most violent electromagnetic signals we can observe from across the cosmos. That coiled magnetic fury isn't something abstract. It's a real, lethal force. Those giant flares we see, those universe-brightening screams from across the galaxy, they carry a sobering implication. They're not just light shows, they're a genuine cosmic hazard, even if it's remote. Research suggests a giant flare from a magnetar, if it happened too close to our solar system, could have severe consequences. The main threat wouldn't be the flash of light. It would be the storm of high-energy radiation and particles that comes after. If a magnetar within about 10 parsecs, that's 33 light-years, if it unleashed an event like that, the blast would hit our atmosphere. The intense X-rays and gamma rays would break apart molecules in the upper atmosphere. They'd target the ozone layer, that protective shield, the one that filters the sun's most harmful ultraviolet radiation. It could be significantly depleted. The ecological impact would be profound. With a weakened ozone layer, surface levels of dangerous ultraviolet light would rise dramatically. That could damage ecosystems. It could harm phytoplankton, which is at the base of the ocean food web. It could affect crop growth on land. The long-term consequences for global biology are serious to consider. It shows how a stellar event tens of light years away could ripple through an entire biosphere. This scenario, it's grounded in solid physics, but it's thankfully not a pressing concern. The nearest known magnetars are thousands of light years away. They're safely beyond this hypothetical danger zone. Our solar system seems to be in a relatively calm stellar neighborhood. We're free from these magnetic monsters in our immediate vicinity, but studying these potential threats, it's not just an academic exercise. It helps scientists define a broader class of astrophysical risks. Things like supernova, gamma-ray bursts. It helps model how life-bearing planets might persist or perish across the cosmos. This research raises profound astrobiological questions. If a galaxy is particularly rich in magnetars, or in the massive stars that create them, could that make entire regions less hospitable for complex life? Planets orbiting stars in dense stellar clusters, or near a galaxy's bustling core, they might face a much higher rate of these extreme radiation events. Their potential biospheres would need to be extraordinarily resilient, or life would need to arise and evolve in brief, quiet windows between these celestial storms. Our own position in a quieter suburb of a spiral galaxy, it may be more fortuitous than we realized. It gives us the stability to study these distant monsters. Not in fear, but with a sense of awe and inquiry, recognizing that our peaceful cosmic address, it's a key part of the story of life here. The power of a magnetar's outburst makes it a prime suspect for another cosmic mystery. Astronomers see these fleeting signals across the deep sky. They last just milliseconds, but in that blink, one burst can release more energy than our sun puts out in 3 days. These are fast radio bursts. Their origin has been one of the most puzzling questions since they were found. They seem to come from galaxies far beyond our own, so the source has to be phenomenally powerful to be seen across that distance. For years, the list of possible culprits was long: colliding neutron stars, evaporating black holes, or something entirely unknown. Then in April 2020, a clue arrived from our own cosmic backyard. A known magnetar in the Milky Way, SGR 1935 plus 2154, suddenly erupted. It wasn't a giant gamma-ray flare. This time it produced a much shorter, incredibly intense spike of radio waves. A millisecond blast that looked identical to the mysterious fast radio bursts from distant galaxies. It was the first time a magnetar was caught producing a signal that bridged a known object and a deep cosmic enigma. The connection is compelling. Think about what happens during a magnetar starquake. The crust cracks, shaking the magnetic field lines. That sudden motion can launch a storm of particles and energy. Or consider magnetic reconnection in the Twisted Magnetosphere, where field lines snap and reconfigure, releasing a catastrophic pulse. Both processes are like striking a bell with a cosmic hammer. The resulting vibration could theoretically produce a coherent flash of radio waves, a fast radio burst. The magnetar has all the necessary ingredients. The strongest magnetic fields in the universe, a constant state of immense stress, and the ability to release that stress in sudden, catastrophic events. It's a natural factory for extreme transients. If this link holds, magnetars aren't just magnetic curiosities. They are multi-messenger monsters. They could be the engines behind some of the most powerful, brief flashes we see across the cosmos. One type of extreme object would help explain another, tying together two great puzzles with a single magnetic thread. The search is on now to catch more magnetars in the act, to see if they can produce the full range of fast radio burst behaviors we observe from deep space. That magnetic thread, it's woven right into the galaxy's fabric. These objects are rare, maybe a few dozen in the whole Milky Way, but their impact is huge. A magnetar isn't just some distant curiosity. It's a local force of nature. It shapes the ecology around it. It starts with energy. The steady X-ray glow from an older one, the catastrophic blasts from a young one. They pour high-energy radiation into space. That radiation doesn't just travel, it slams into the gas and dust drifting between stars, the interstellar medium, and that collision does something. It heats the gas, it ionizes it, strips electrons away, creates a hot, charged plasma bubble around the magnetar. This heated region pushes against cooler, denser clouds. Alters their chemistry, their dynamics. A magnetar acts like a cosmic blowtorch, carving out a cavity in the galactic clouds. That process can stifle star formation nearby. For a new star to form, a gas cloud needs to collapse under its own gravity. But if that cloud is being heated and stirred by radiation from a magnetic monster, the collapse can be prevented. The cloud stays puffed up, too energetic to condense. So in one way, magnetars might be guardians of empty space, keeping their local nurseries quiet. But their influence isn't only destructive. The shock waves from their giant flares, moving out for light years, can have the opposite effect. When a powerful shockwave plows into a massive, cold gas cloud, it doesn't just heat it uniformly. It can compress it in certain areas, create dense, rippling sheets and filaments, and in those compressed pockets, gravity can finally win, triggering a new wave of star formation. So a single catastrophic event from a magnetar could paradoxically be the midwife for a new generation of stars far away. They are both agitators and architects. Their most spectacular outbursts also add to the galaxy's chemical richness. Theoretical models of giant flares suggest the insane temperatures and densities in those magnetic fireballs could host exotic nuclear reactions. Processes that forge heavy elements, atoms heavier than iron, through rapid neutron capture. It's the same type of process believed to happen in neutron-star collisions, but smaller. More frequent, each giant flare could, in principle, seed its surroundings with a fresh dusting of rare, heavy elements. Over millions of years, across countless flares from different magnetars, this could be a meaningful source of galactic enrichment. It means the gold in a wedding ring, the uranium in a power plant, their origin might include not just supernova and neutron star mergers, but also the magnetic fury of these extreme objects. So it paints a picture. A magnetar isn't an isolated freak. It's a dynamic component of a living galaxy, a cosmic lighthouse whose beam does more than signal. It heats, it stirs, it compresses, it sprinkles new elements into the void. Its magnetic influence, born from stellar death, becomes a subtle but persistent hand in the story of cosmic evolution. Scientists use supercomputers to rebuild that moment a magnetar is born. They're building one from the equations. This is computational astrophysics. It's one of the hardest problems in science. The issue is scale. You're modeling a stellar core collapsing. You track matter from the size of a planet down to a city in less than a second, and you have to follow 3 sets of physical laws at the same time. First, gravity. At these densities, Newton doesn't work. You need Einstein's general relativity. The curvature of spacetime warps everything. Second, the fluid. It's a super-hot, conductive soup that's governed by magnetohydrodynamics, the equations for how magnetic fields and fluids twist together. Third, the quantum nature of matter itself. At nuclear density, you need equations of state. They describe how protons and neutrons behave under pressure that crushes atoms. Getting these 3 physics to talk to each other in a simulation that runs for a realistic time takes staggering computing power. Supercomputers divide the virtual star into hundreds of millions of cells. They calculate the forces in each cell at each tiny slice of a millisecond. The goal is to watch the dynamo emerge, to see if the chaos from the collapse, the differential rotation, the shearing, can amplify a magnetic field to magnetar strength. These simulations are our only virtual labs. Researchers test the model by changing variables. What if the star spun faster? What if the magnetic field started weaker? Each run is a cosmic what-if. It costs millions of processor hours. Sometimes the simulations succeed. They show a powerful, organized magnetic field rising from the digital chaos. Its strength climbs into the magnetar range. It's a validation, a sign the theoretical blueprint might be right, but the simulations also show the limits of our knowledge. The biggest uncertainty is the equation of state. That's the math for how matter behaves at densities we can't create on Earth. Is the core a soup of free quarks? A lattice of hyperons, each possibility changes how the fluid flows and conducts. It changes how it sustains a magnetic field. The simulations have to try them all. The results can be dramatically different. A magnetar might form under one equation of state but not another, so every simulation is a double quest. It tests our theories of stellar collapse and dynamos, and it probes the fundamental nature of matter itself. Each time the supercomputer finishes a run, we're not just looking at a possible star history. We're glimpsing the rules of physics under the most extreme conditions the universe can make. The digital magnetar is a guide. It points toward truths we can't yet reach, but are determined to understand. Before 1992, that idea wasn't there. We knew about neutron stars. We knew they were magnetic, but a separate class, something 1,000 times stronger, that wasn't part of the picture. Then two astrophysicists, Robert Duncan and Christopher Thompson, they looked at the equations. They followed the logic of stellar collapse, dynamos, quantum matter. And the math told a story the observations hadn't caught up to yet. It said that under the right conditions, fast spin, turbulent convection, a neutron star could amplify its magnetic field to a level we hadn't imagined. They gave that predicted object a name, a magnetar. For years it stayed a prediction, a compelling idea from theory, waiting for the universe to show a match. It was a solution looking for a problem, an answer waiting for its question in the sky. To a lot of people, it seemed like a fascinating speculation. Maybe too extreme. Could nature really be that violent, that efficient at making magnetic fields? Then the universe answered, not with a whisper, with a scream that shook our detectors. The soft gamma repeaters, the anomalous X-ray pulsars, they were being studied. Their strange behavior was catalogued but not understood. They were the questions. And in December 2004, one of them, SGR 1800620, it gave the definitive answer. It unleashed a giant flare, so powerful it temporarily changed Earth's upper atmosphere from 50,000 light-years away. In that moment, the theoretical magnetar stepped off the page into reality. The object's behavior, its spin-down rate, the sheer energy of the outburst, it all fit the Duncan and Thompson model perfectly. The prediction had been precise. This journey, from a line of equations on a whiteboard to a confirmed, raging entity in our galaxy, it's a beautiful example of the scientific process. It shows how human curiosity, guided by rigorous theory, can anticipate nature's most extravagant creations. Long before our telescopes catch up, it changed our understanding of neutron stars forever. They weren't just cosmic lighthouses anymore, not just precise clocks. Some of them were coiled springs, springs of magnetic fury, a new and terrifyingly powerful breed of stellar remnant. The discovery validated something profound about our universe. If the physics allows for something, no matter how extreme, the universe will eventually build it. Our task is to be clever enough to see it and patient enough to recognize it when it finally shows itself. A quadrillion-Gauss, that number, it's so large it just stops meaning anything. But you only feel its weight when you put it next to something else. Take our own planet, this blue marble wrapped in its magnetic cocoon. That field, the one that guides compasses and shields us from solar storms, it measures about half a Gauss. Just a gentle whisper, a life-sustaining whisper. Then, on the Sun, in the dark heart of a sunspot, magnetic forces can get up to a few thousand Gauss. That's powerful, powerful enough to shape solar flares, coronal loops, a localized roar on the star's surface. Then you leap to a neutron star, the corpse of a giant, spinning, beaming radiation. Its magnetic field is typically around 1 trillion Gauss, a 1 with 12 zeros. This isn't a force that just influences anymore. It dominates. It accelerates particles to near light speed. It carves the space around it into a tortured magnetosphere. That field is 1 billion times stronger than a sunspot's. It exists in a realm of physics we can't really replicate. But for a magnetar, that trillion Gauss mark, that's just the starting line, the baseline. A magnetar's field measures roughly a quadrillion Gauss, a 1 followed by 15 zeros. So a magnetar's magnetic grip is another 1,000 times stronger than an already unfathomable pulsar. To see that leap, think of the difference between the gentle tug of a refrigerator magnet and the crushing, containment-level force inside the world's most powerful experimental fusion reactor. That's the scale, the jump from a pulsar to a magnetar. It's not just a bigger number, it's a fundamental shift in the state of existence. At a quadrillion Gauss, magnetic pressure becomes the absolute ruler. It overwhelms gravity, it warps the quantum vacuum, it can literally bend the fabric of space-time around the star. This comparison, it does more than just catalog cosmic strengths. It draws a bright line in the sand of physical extremity. On one side, you have all other magnetic objects, planets, stars, even most stellar corpses. Their magnetism is a powerful feature of their environment. On the other side stands the magnetar, alone. Here, magnetism isn't a feature, it's the entire identity. It's the engine, the architecture, the apocalyptic weapon. This unique category tells us something, that the universe reserves a special kind of violence for its most extreme creations. Where force isn't just applied, it becomes the very essence of being. 24 of these monsters in a galaxy with hundreds of billions of stars that makes the hunt daunting. Finding more isn't just about cataloging oddities, it's about testing our theories, how they form, their life cycle, their real impact on the galaxy. To do that, astronomers have to scan an immense dark ocean. They're looking for brief, brilliant flashes, the flashes of these particular leviathans. The main tool for the search is the X-ray eye. Magnetars announce themselves most loudly in X-rays, whether in a violent outburst or just a steady, heated glow. Space-based observatories act as our sentinels. Chandra, XMM Newton, NASA and Neil Gehrels Swift Observatory. Some searches look for the sudden bursts. The unpredictable ones, those starquakes or magnetic reconnection events that send a spike of X-rays across the galaxy. It's like listening for a shout in a silent forest. Other surveys look for something else, persistent, bright X-ray sources with no visible counterpart. You point an optical telescope at that exact spot. And you see nothing, no star, no galaxy, just darkness. That absence of light is a clue. It suggests the object is small, incredibly dense, pouring its energy out in a form our eyes can't see. A brilliant, city-sized ember glowing in X-rays alone. That's a prime magnetar candidate, but a bright X-ray source isn't proof. The next step is follow-up. Astronomers train other telescopes on the candidate. Long, careful observations. They need to measure its heartbeat, its spin period. They watch for the regular pulse of X-rays. As the hotspot on the magnetar's surface rotates in and out of view, that reveals the spin, often slow, maybe once every 2 to 10 seconds, then with even more patience. Observations over months or years, they measure how that spin is changing. They clock the spin down. How many milliseconds longer does each rotation take? That tiny, precise measurement of slowing is the key, the golden key. You plug that spin down rate into the equations. It reveals the power of the magnetic brake being applied. It calculates the field strength, and when that calculation spits out a number in the Quadrillion-Gauss range, the candidate earns its title. It's confirmed. A magnetar, now a new generation of instruments, is opening a fresh window into their hidden architecture, the Imaging X-ray Polarimetry Explorer, IXP. It measures something previously untapped, the polarization of X-rays. Think of light as a wave. Normally, these waves vibrate in all directions, but when light comes from a highly structured magnetic environment, those vibrations get aligned. They become polarized. By measuring this polarization in the X-rays from a magnetar, IXP can map the geometry of the magnetic field at the source. It can tell us if the field is a simple dipole, like a bar magnet, or a complex, twisted wreckage of braided lines. This isn't just a new detail. It's a direct test of our models of magnetospheric physics. It can show us how the energy is truly channeled, where the instabilities that lead to giant flares might originate. Each new magnetar found is a data point, each new property measured. It helps us understand what special blend is required. The blend of spin, mass, and chaos needed to forge these objects. It tells us if they're truly rare accidents, or a common, hidden phase in the life of many neutron stars. The hunt continues, not just for more monsters, but for a clearer picture, of the magnetic frontier of our universe. That magnetic grip that drives their violence also gives them a kind of calm. In their quiet phases, some magnetars settle into a rhythm, a very stable one. Their slow, steady spin becomes like a cosmic metronome. It ticks with a precision that rivals the best pulsar clocks, even surpasses them. That regularity turns them into more than just objects to study. They become instruments. By tracking their X-ray pulses over years with nanosecond accuracy, astronomers aren't just watching a star. They're reading a message, a deeply encoded one about the nature of reality. Every pulse is a data point in a grand experiment. As the magnetar spins, if its motion is disturbed even a tiny amount, that shows up as a minuscule shift in the timing. What could cause that shift? One possibility is the passage of a gravitational wave. These ripples in space-time, predicted by Einstein, they stretch and compress the very distance between the magnetar and Earth. When space stretches, the light pulses take a fraction longer to reach us. When it compresses, they arrive a fraction sooner. So by monitoring an array of these stable magnetar clocks scattered across the galaxy, scientists could detect the subtle symphony of low-frequency gravitational waves. Waves that might be coming from mergers of supermassive black holes or from cosmic strings left over from the universe's birth. A single magnetar clock tells time. But a network of them could listen to the background hum of the cosmos, and the tests go deeper. The immense gravity of a magnetar, combined with its precise rotation, creates a natural laboratory for testing general relativity under conditions we can't recreate. Einstein's theory makes specific predictions about how a massive, spinning object should drag the frame of space around with it. That's frame dragging. It predicts how gravity should affect the timing of signals. So by meticulously analyzing the pulse timing from a magnetar, researchers can look for deviations. Any discrepancy could be a sign of new physics, a hint that our understanding of gravity needs revision. In these most extreme environments, this dual nature is what makes them compelling. They are both cataclysm and chronometer, the source of the most violent explosions we know, and yet also among the most stable timekeepers in the galaxy. That paradox turns them into unique portals. Their fury reveals the limits of matter and magnetism. Their quiet, unwavering tick probes the fundamental laws. Listening for whispers in the space between the stars, mapping a magnetar's interior, it's like an impossible crime scene. You can't see inside, you can't send anything in. The pressure and density they're so extreme. The matter exists in forms we can't replicate here. So how do you chart it? You listen, you feel for vibrations. When the crust cracks in a starquake, it doesn't just snap, it rings like a bell. Those oscillations, those seismic shudders moving through the layers, they leave a fingerprint on the X-ray light we get. The brightness flickers in a specific pattern, a rapid pulse inside the pulse. That field is asteroseismology. Decoding those flickers, you can deduce details. The frequencies tell you about the crust's thickness, its elasticity. Is it a thin, brittle shell or something thicker, more rigid? And the way the vibrations dampen, how they fade, that shows how energy is absorbed by the layers underneath. It's like tapping on a wall and listening to the echo. Each starquake is an accidental experiment. It sends a pulse of information through the unseen interior, out to our telescopes. Then there's the star's temperature, not the surface, the deep, internal heat. A magnetar glows in X-rays partly from its decaying magnetic field, but also from the residual warmth of its birth. Billions of degrees trapped inside. By measuring how quickly that X-ray glow fades over years, the cooling rate, scientists can run models. If the core were normal neutrons, how fast should it cool? What if it were a soup of free quarks or a lattice of exotic hyperons? Each interior composition transfers heat differently. Some would let the warmth escape quickly. You'd see rapid cooling. Others would act as insulators, keeping the star hot for millennia. The observed cooling rate measured over years acts as a filter. It rules out some theories of dense matter. It gives weight to others. It's a thermal whisper from the core, a whisper about its fundamental makeup. The future holds a promise. An even more direct sense, sound, not sound in air, but vibrations in space-time itself. A truly colossal starquake, one that distorts the magnetar's shape, could generate gravitational waves. Ripples moving at the speed of light. Detectors like LIGO and Virgo are listening for these tremors. If they ever catch the signal from a magnetar oscillation, it would be a revolution. A literal recording of the star's interior vibrations. The frequency and amplitude of those waves would encode the core's density, the stiffness of the matter. The equation of state, it would be like placing a stethoscope against the star's heart, hearing its beat for the first time. These methods, the seismic echoes, the thermal history, the hope for gravitational songs, they're each a different piece of the puzzle. Multi-messenger keys to an invisible lock. Together, they let us slowly draw the map of a place we can never visit, a map of the ultimate magnetic forge. Written in vibrations and heat and the bending of space itself, a magnetar story is about fading light. It starts with the supernova, that instant of ultimate violence. In that first second, the magnetic field is at its absolute peak, a coiled spring of pure force wound impossibly tight. That's the explosive infancy. Then for the next few thousand years, it lives as a true monster, its active youth. It shows up as either a soft gamma repeater or an anomalous X-ray pulsar. The SGR is the temperamental adolescent, prone to violent outbursts, giant flares, its crust fracturing under the stress. The AXP is the quieter sibling, glowing with a steady, heated X-ray radiance, its power bleeding away in a more constant stream, but both are fueled by the same reservoir, that unimaginably strong magnetic field, slowly converting its stored energy into light and heat and particle storms. No reservoir is bottomless. Over millennia, magnetic decay takes its toll. Electrical resistance in the crust, drifting and annihilation of magnetic vortices in the quantum core. They act as a steady leak. The field's strength diminishes bit by bit. As the magnetic break weakens, the star's spin-down slows. Its furious rotation, inherited from its chaotic birth, gradually winds down into a more sedate rhythm. The outbursts become less catastrophic, less frequent. The starquakes grow milder. The crust is no longer stretched to its absolute breaking point. The brilliant X-ray glow begins to dim. After maybe 10,000 years, a transition occurs. The magnetic field decays below the Quadrillion-Gauss threshold, the line that defines a magnetar. It's still monstrously strong, 1 trillion times Earth's field, now a powerful pulsar, but it has crossed that line. The internal stresses aren't enough anymore. Not enough to drive the giant flares, the extreme behavior of its youth. The magnetic spring has mostly unwound. The monster settles into a kind of magnetic senescence. It becomes a more ordinary neutron star, still a cosmic powerhouse, still a precise celestial clock, but no longer the universe's premier magnetic extremist. This life cycle is a crucial piece. It connects magnetars directly to the broader family of neutron stars. They're not a separate, alien breed, they're a phase. A brilliant, violent, temporary stage in the long existence of a stellar corpse. A neutron star may be born as a magnetar, live its spectacular magnetic life, then spend the next hundreds of thousands of years as a quieter pulsar, its light eventually fading into the dark. That view transforms them from static oddities into dynamic, evolving characters in the galactic story. It shows a fundamental truth about the cosmos. Nothing is permanent, not even the strongest forces in the universe. They too are born, they blaze, and they slowly, inevitably fade. That final, faint light from a magnetar in its old age, It's nothing like how it starts, because the way a magnetar is born can be incredibly violent. It might not be quiet at all. It could be the engine for one of the universe's most powerful explosions, a long gamma-ray burst. For a long time, the main idea was that these bursts came from a star collapsing straight into a black hole. A stellar core too heavy to become a neutron star just gives way. It forms a black hole, and as matter falls into it, it launches these powerful jets. They rip through the rest of the star and blast out into space. Those jets, moving almost at light speed, are what we see as the gamma-ray flash. But there's a problem. Some of these bursts, the longer ones, they have this strange afterglow, a steady X-ray glow that can last for minutes, even hours after the main flash is gone. That leftover energy is hard to explain if the engine, the black hole, has already eaten most of the fuel and shut off, so that's where the magnetar idea comes in. Think about that massive star collapsing. Its core implodes, but instead of going all the way to a black hole, it stops just before. It forms something else. A neutron star, but not a normal one spinning as fast as it can, hundreds of times a second, with a magnetic field already in the magnetar range. A millisecond magnetar, this new object is full of spin energy. It's rotating so fast it's vibrating, and it's wrapped in that unbelievably strong magnetic field. That combination makes a different kind of engine. The fast spin plus the intense magnetism can drive a powerful wind, a wind of particles and radiation that keeps pumping energy into the jets long after the initial collapse. It's like a battery keeping the gamma-ray burst shining. This explains that lasting X-ray afterglow. The magnetar's spin is being slowed by its own magnetic field. That braking turns the star's rotation energy directly into the energy fueling the jet. We're seeing a cosmic top slowly spin down, its energy becoming a light we can see across the universe. It connects two extreme things. The catastrophic death of a giant star doesn't always make a black hole right away. Sometimes it forges a magnetic monster first. And for a short, brilliant moment, that monster's furious spin powers a light that can outshine a million galaxies. The birth of a magnetar might be the brightest flash there is. The quantum vacuum isn't empty. It's a sea of potential, a roiling foam where particles and their antimatter twins flicker in and out of existence, all within the rules of quantum uncertainty. It's a foundational concept, but it's invisible under normal conditions. To see its effects, you have to push reality to an extreme. You need a force strong enough to reach into that foam and pull. That force is the magnetic field of a magnetar. At a quadrillion-Gauss, the field is so intense it doesn't just influence matter. It warps the very nature of the space around the star. It stresses the quantum vacuum itself. In that environment, the vacuum changes. It becomes an active medium, one that can alter light passing through it in strange, measurable ways. One predicted effect is vacuum birefringence. In an ordinary crystal like calcite, birefringence splits a light beam into two rays, each traveling at a slightly different speed. The magnetar's magnetized vacuum does something similar, but not with a crystal. It uses pure magnetic force. Light is an electromagnetic wave, and its vibrations can be oriented in different directions. It's polarization. In the magnetized vacuum near a magnetar, light polarized parallel to the magnetic field lines interacts with the quantum foam differently than light polarized perpendicular to them. This difference means the two polarizations actually travel at different speeds. One gets a tiny head start over the vast distance from the magnetar to us. That microscopic delay could leave a detectable imprint on the light we receive. Another predicted phenomenon is vacuum dichroism. This is where the magnetized vacuum doesn't just slow light differently, it absorbs one polarization more than the other. It acts like a cosmic filter, subtly dimming one orientation of light as it passes through this tortured space. These aren't just theoretical curiosities. They are specific, quantitative predictions made by quantum electrodynamics, our most rigorously tested theory of how light and matter interact. But these effects are so faint they only become significant in the strongest magnetic fields in the universe. Magnetars provide the only natural laboratory where we might hope to see them. The key to the search is polarization. We now have telescopes like the Imaging X-ray Polarimetry Explorer that can measure the polarization of X-rays from cosmic sources. By carefully analyzing the polarized light from a magnetar, astronomers are looking for the subtle signatures of these vacuum effects. They are searching for patterns in the polarization that can't be explained by the hot plasma or the twisted magnetic fields alone. They are looking for the fingerprint of empty space itself, bent and stretched by a force of mythical strength. Finding that fingerprint would be a monumental discovery. A direct observational validation of quantum field theory in a regime we can never hope to recreate on Earth. It would turn the space around a magnetar into more than just an environment. It would become a fundamental physics experiment built by the cosmos, running continuously for millennia. Every photon of X-ray light that journeys from that magnetic monster to our detectors carries not just information about the star, but a potential message about the deepest, most elusive fabric of reality. We are just learning how to listen. The power of a magnetar is so immense it feels almost fictional, like something from a myth. It's no wonder they've jumped from scientific papers into our stories. Science fiction writers use them, game designers use them. They become the ultimate power source for a civilization, or a hazard that can rip ships apart from light years away. Or a trigger for a cataclysm. In these stories, the magnetar isn't just a star. It's a plot device, pure possibility. This reflection is fascinating. It shows a pipeline from the cutting edge of astrophysics straight into our creativity. The real science is there, the magnetic fields, the quantum vacuums. That science becomes a scaffold, something for the imagination to build on. When an author writes about a ship using magnetar flares to jump dimensions, or a game has you harvest energy from a dying star, they're doing more than telling a story. They're performing a translation. They take complex, abstract theories and wrap them in a language we know. Adventure, danger, discovery. That translation has a purpose. An educational one. For a lot of people, their first encounter with a neutron star or a magnetic field that bends light won't be in a textbook. It'll be in a novel. Or a film or a game. That initial spark is invaluable. That moment of thinking, that's incredible, could that be real? It breaks down a barrier, the barrier between intimidating science and public wonder. Someone might watch a hero navigate a magnetar's magnetosphere in a movie. Then later, they hear a real astronomer talking about these objects, and they have a reference point. A touchstone. The fiction built a bridge, and this cycle, this back and forth, it fuels science itself. The young person staying up late reading a space opera about magnetars might be the one who, years later, sits at a console analyzing data from a deep space telescope. They look up at the same stars from those stories, and they ask the question that drives science forward. They ask, what if we could really map that magnetic field? What if we could understand the matter at its core? The line between science fiction and science fact has always been porous. Each one feeds the other. A loop of inspiration. By dreaming of magnetars, we learn to measure them, and by measuring them, we find new dreams, even more incredible ones. The hunt for these magnetic monsters is about to get its most powerful tools. Our understanding, built from flashes and whispers, is ready for a leap. The next observatories won't just look at magnetars, they'll listen to them. Feel their vibrations, dissect their light with a kind of surgical precision. Leading that charge is the European Space Agency's Athena, an X-ray observatory. It's slated for launch in the 2030s. Athena's vision is revolutionary. Its X-ray eyes will be 100 times more sensitive than anything we have now. So it won't just see outbursts, it will study their spectra, the detailed fingerprints of light during the quiet moments and the violent flares. Imagine reading the fine print on a starquake's energy from 50,000 light-years away. Or mapping temperature variations across a magnetar's surface in real time as it cracks. Athena turns our blurry snapshots into a high-definition movie. It reveals the physics of magnetic reconnection and particle acceleration as it happens. Beyond light, a new sense is waking up, the Laser Interferometer Space Antenna, LISA. A future gravitational wave observatory that will float in space. Ground-based detectors like LIGO listen for the high-frequency chirps of colliding black holes. But LISA is tuned to a lower register. It will hear the constant hum and rumble of the cosmos, and in that symphony there might be a distinct note, the ringing of a magnetar. A truly colossal starquake, one that shakes the star's very shape, would send ripples through space-time. LISA could sense those tremors. It would be the most direct measurement possible of a magnetar's interior oscillations. A literal recording of its seismic heart. Combine that gravitational soundtrack with Athena's X-ray video, and you get a multi-messenger portrait of unprecedented clarity. On the ground, radio and optical telescopes keep evolving. Their networks grow more sensitive, more coordinated. The goal is to catch a magnetar in the very act of being born. To witness the supernova or the neutron-star merger, to see the magnetic monster emerge from the chaos in real time. That would be the ultimate test of our dynamo theories. We could watch the magnetic field amplify before our eyes, measure its growth second by second as the newborn star takes its first breaths. These future missions are more than just better data. They signify a shift in how we probe the universe's extremes. We're moving from passive observation to active, multi-dimensional sensing. By weaving together X-rays, gravitational waves, and light, we won't just describe magnetars. We'll begin to truly understand them. We'll test the limits of quantum electrodynamics in their magnetospheres, probe the equation of state in their cores, trace the complete life cycle of magnetic energy from catastrophic birth to quiet old age. A new era of discovery is on the horizon. One where the universe's strongest magnets will finally have to reveal their deepest secrets. But with every answer we get, the magnetar just gives us more questions. We've got the broad picture of how they're born and how they live, but the fine details are still hidden. It really comes down to the core itself. We call it the equation of state. It's this mathematical description of matter at densities that are 100 trillion times greater than water. And we don't know what it is. Is it a superfluid of neutrons or a crystalline lattice made of exotic particles, hyperons? Or could it be a soup of free quarks, just the fundamental building blocks swirling around? Our best simulations give different answers. Depending on which equation you use, you get a different maximum mass for a neutron star, a different cooling rate, a different way it conducts magnetic fields. Until we can actually see inside, the magnetar's heart is just a theoretical landscape, a map with several possible routes. The next generation of gravitational wave observatories might feel the core vibrating. That could be our first direct clue. Then there's where they come from. The classic story is a supernova from a massive, fast-spinning star. But could a magnetar also be born when two neutron stars merge? In that hypermassive remnant that exists for just milliseconds before it becomes a black hole, could a magnetic field get wound up to magnetar strength in that instant? Some short gamma-ray bursts, some unusual chemical signatures out there, they hint that this might be a second pathway, a rarer one. If that's true, then the universe has two forges for these magnetic monsters. Each with its own signature we haven't fully decoded yet. Even their biggest explosions, the giant flares, we don't fully understand. we know they involve a catastrophic release of magnetic energy. But what's the precise trigger? Is it a sudden crack that goes through the entire crust, like an earthquake on a planetary scale? Or is it a reconnection event high up in the magnetosphere, where twisted magnetic field lines snap and rewire themselves? That releases a firestorm of particles. The light we see is the aftermath. The initial spark is still hidden. It's behind an avalanche of radiation. And then, how does that magnetic energy convert so efficiently into the blinding light we see? The process has to involve billions of electrons being accelerated to nearly light speed in a coordinated way, and then radiating in unison. It's like getting an entire stadium to clap in perfect rhythm. But instead of hands, it's fundamental particles, and instead of sound, it's X-rays you can see across the galaxy. That conversion from stored magnetic force into coherent radiation, it's a masterpiece of physics. And we're still learning how to read it. These open questions, they're not just gaps, they're the engine. Each mystery is an invitation, a cosmic puzzle box. They drive the design of new telescopes, they drive new simulation code, they drive those late nights sifting through data for one anomalous signal. The story of magnetars isn't finished. And that's what makes it compelling. This whole journey to understand them, it's just a testament to that basic, relentless human urge to look into the cosmic dark, find the brightest points of mystery, and shine a light. It starts with a star, a massive one, many times heavier than the sun, and spinning fast. That spin is important. It's momentum that gets passed on. When that star runs out of fuel, gravity wins. The core can't hold itself up anymore. It collapses. That's the supernova. In that collapse, a few things happen. The star's original magnetic field doesn't disappear. It gets trapped, and as the matter is crushed down from a planet's size to a dozen miles across, the field is crushed with it, compressed by billions. That's magnetic flux conservation. It takes a strong stellar field and makes it a seed of magnetic potential. What's left is the hot, dense heart. A proto-neutron star. It's born spinning incredibly fast, just milliseconds per rotation, taking the spin from its parent, and it's full of trapped heat. For a brief window, maybe 10 or 20 seconds, this new object isn't quiet. Inside, it's a churning ocean, a quantum fluid of neutrons and protons and electrons at billions of degrees. That heat drives violent convection, bubbles rise and sink, and at the same time, different layers are spinning at different speeds. The crust might try to slow, but the liquid interior keeps whirling. That difference creates shearing forces, so you have this compressed magnetic seed placed into this environment, a super-hot, conductive fluid caught between turbulent convection and extreme shear. That combination is the super dynamo. It's an engine. The chaotic motions grab the magnetic field lines frozen in the fluid. They stretch them, they wind them. Like twisting rubber bands, tighter and tighter. With every turn, the kinetic energy of the spin and the thermal energy of the heat get pumped into the magnetic field, amplifying it exponentially. In those few seconds, the dynamo does its work. It forges a magnetic field of legendary power, reaching the Quadrillion-Gauss realm. That's what defines a magnetar. The storm inside then begins to fade. The heat leaks away. The differential rotation settles, but the magnetic monster it created remains. Bottled and preserved by the star's own superconducting core, the result is a stressed object, a city-sized ball of nuclear matter wrapped in a cage of magnetic force. This magnetic personality, imprinted at birth, dictates everything. It powers the steady X-ray glow of an anomalous X-ray pulsar. It builds the stress that cracks the crust in starquakes. That unleashes the soft gamma-ray bursts of a soft gamma repeater, and in rare events, it reconfigures itself in a giant flare, one that can outshine galaxies. That's the violent life of a magnetar, a consequence of its forged magnetic soul. But even this power isn't eternal. the magnetic field that coiled spring slowly unwinds over millennia. Through electrical resistance in the crust, through the slow drift of magnetic vortices in the quantum core, the energy gradually converts to heat and radiates away. The outbursts become less frequent, the glow dims. After tens of thousands of years, the field decays below that extreme threshold. The magnetar phase ends. It transitions into a more ordinary neutron star, but its mark is there. In its active life, it heated interstellar clouds. It triggered or suppressed star formation. It may have seeded space with heavy elements. Its story, from a specific stellar beginning to magnetic dominance and then quiet, is a complete arc. It shows how the universe can concentrate the chaos of a dying star into a focused force. One that shapes its corner of the galaxy. They're not just points of light, they're monuments, testaments to extreme forces. The story starts with a stellar collapse, that violence. Then it moves into a quantum soup where matter changes, and it echoes across the galaxy in flashes you can see from millions of light years away. They're like cosmic laboratories. Pushing physics to a breaking point, every starquake, every X-ray glow is a data point, an experiment the universe is running. To understand them is to ask the deepest questions. About matter, energy, space, and time. This quest to map their magnetic hearts, it does more than satisfy curiosity. It refines the rules that govern everything. From a compass pull on Earth to the warped vacuum around a dying star, the journey shows a cosmos that's dynamic, often violent, breathtakingly complex in its beauty. As telescopes sharpen and simulations improve, the magnetar story will keep evolving. New mysteries will come out of the data, each one an invitation to look deeper, to question further.